So we start first now with Dr. Gautam Shroff. Dr. Gautam Shroff is Senior Vice President, TCS Fellow, and also Head of TCS Research, Data Consultancy Services. He would be speaking on AI and deep learning in an uncertain world.
Okay, thank you for that introduction and for inviting me for this meeting. So I'm going to talk about AI and deep learning, but in particular, the context is the sudden uncertainty that we have found ourselves in, and leveraging it. But what if the data was in a different world, which doesn't necessarily exist? It's turned out that this particular dichotomy or this problem has brought out some basic fundamental gaps which have been well known in AI. It's just brought them to the fore. So I'll try to highlight some of these issues with very few simple examples without getting into any technical details. Okay, let's see. Right. So obviously there's a lot of buzz. Every year we have a hype cycle, and AI has its own hype cycle, and some things are new and some things are becoming old. And there's a lot of hype. Clearly, the news, the clickbait on your phones, it's all was all about AI till the pandemic hit, and now of course been overshadowed by perhaps more pressing things. But even otherwise, there have been a lot of expectations. So there were many panels set up by the government. I was on one of the first one of them. We were submitting a report way back, two and a half years back, I think. And then there were many other panels after that. Many expectations on how it would change things drastically, perhaps exaggerated expectations at some point. And also many fears. One fear was jobs, which we sort of addressed in our report a bit. Another fear was global, whether we would have robot killer weapons. And I was on a panel at the UN where we were trying to regulate these things, but obviously not every country wanted it regulated. But then anyway, there's a lot of hype, there's a lot of expectation and fear. But the reality, I think, in a sort of a considered view, is rather different. And I'll now turn to a few examples. So what does AI actually allow people to do, or allow machines to do? I mean, let's just get to the basics. There's this AI really started off with sort of good old-fashioned AI, which is all about logic and logical reasoning. And it's been put aside in some sense these days. People aren't looking at it enough, but as I'll explain, it's getting more and more important. And even the gurus of deep learning are now realizing the benefits of some of these things. And I'll give you a few examples. Secondly, of course, machine learning and deep learning have had their remarkable successes in perception, recognizing things, images, faces, etc., processing natural language. I won't use the word understanding, but certainly processing natural language to glean and extract information from it. And then, decision making, predicting, not decision making, but say predicting things in the future, predicting what people will do, predicting how many things will be bought, or what will happen to a machine, and things like that. So the deep learning has been extremely good at this. And lastly, decision making. Reinforcement learning has helped us do these things. Now, if you don't understand all these things, it's fine. I know the audience is broad and vast, and perhaps many of you do. But this is the broad, and I'll just go through a couple of examples of each of these and talk about how the things change in the current scenario. Okay, so let's start with logical reasoning and perception. So there are two schools of thought here, or schools or approaches. One is you have logical reasoning and you have perception, which is best done through deep learning. And of course, the core fundamental AI question is, how does logical reasoning actually arise from perception? And I don't think we have a great answer, but we're trying to get there. But the point I wanted to make is these are two very different questions. For example, let's take a look at this very simple problem that by understanding familiar relationships. From deep learning way of doing this would be just give a machine learning model thousands and thousands of such examples and answers, and it should figure out not only how to parse a sentence and understand what it's trying to say, but also understand the whole set of possible familiar relationships, second cousins, mamas, chachas, etc., which come in the corpus. And if something was not in the corpus, then the machine learning method would not work, would not understand it. The other way of doing it would be to say, look, if, for example, if you had a logical reasoning engine, you could easily solve this with almost exact accuracy, provided you were able to parse the sentence to get the logical facts out. So that's logical reasoning plus perception would do a great job. But trying to get the logical reasoning out from the perception directly, we still haven't done it yet. There's obviously lots of effort going on in that direction. But from an engineering perspective, one has to understand that these are two very different goals. Let's take a look at a practical example from the world I come from. Suppose out what the amounts are, what the items are, what the addresses are, what the billing is, and all that stuff, right? Well, it turns out that this can easily be done using deep learning. You get about 80-85% accuracy, but we can actually do it with almost 100% accuracy using logic and perception together. Plus, you also want to deal with things like this, where there's handwritten text, and deal with things which might not even be an invoice at first glance, but a human being reading it would immediately know it is an invoice. So what you do here is you use perception to actually extract what you can using image analysis or image-based deep learning or deep learning-based image processing, and actually populate facts or database. And then you do logic reasoning on that, and you get extremely good accuracy. I'll turn to this a little bit later, but this is an example that logical reasoning from perception is a great AI goal, but from an engineering perspective, might not be the best way to approach a problem that you need to solve today, and somebody is going to benefit from it. The second example I'll take is predicting behavior. This has been the sort of mainstay of AI and why it's been extremely successful, machine learning and deep learning in particular. We know when we go to an e-commerce site, pretty much what the site tells us is what we really want, except for the small problem of retargeting, which is an issue. But today's systems are pretty good. However, it turns out that fashion items at all. Who wants to wear a suit on a Zoom call, right? Who wants to wear fashionable clothes when there are no parties? So the entire distribution of what people are buying and who's buying what changed. So what I bought in 2019 has no relationship to what I really want to buy now. And the question is, all that great old data that is kind of useless now. So what do? We have to not only deal with this in AI as a problem, but it also brings to fore a very fundamental problem that has been plaguing machine learning, which is out of distribution generalization. So when the distribution changes, you don't generalize well. Most of the time, the distribution didn't change, so it was sort of a non-problem. But now it's changing every day. So tomorrow there's a lockdown, it changes. Tomorrow it goes away, it changes again. So, well, there are ways of looking at this, and the broad technique is called metalearning. And rather than get into any technical details, the basic difference, in my view, between metalearning, machine learning, traditional ways of doing things, and metalearning is a very simple difference. It's a difference. So here, I went to its namesake, sort of. This is the ITI. I went to IIT. Of course, many people mistook us from as students of the ITI. Well, the ITI teaches people to do a task extremely well and does it really well. It teaches them to weld, it teaches them to do carpentry, etc., etc. But a university like Ashoka doesn't perhaps teach a particular task very well, but it teaches you how to category the traditional machine learning. You can train systems to do a very task very well, like predicting what people will buy, but not figuring out that the buying pattern has changed and you should do something different. So there are, of course, different ways of doing meta learning. I won't go into that here. But that is just one big field which has become ever so more important because of the rapid changes in the way data is behaving. For example, you could do meta learning by simply training a system to do many tasks, or you could do meta learning by trying to extract logical rules from perception, and do that. So there's a whole bunch of stuff going on in this area. I'll now come to decision making. Optimization of some sort. I mean, decision making and optimization, managing supply chains is a very important part. And in the past few years, reinforcement learning has been successfully used in the field to optimize supply chains, to optimize inventory, optimize logistics and shipping, packing at the lowest level, pre-picking in a distribution center, pre-ordering, things like that, right? For example, there are cases where goods are on a route being delivered, ready to be delivered before the order for that particular item has been placed. It's possible because you are able to predict with such accuracy based on past data. Of course, that doesn't work in the current situation. We had situations where a large retailer would have ordered huge amounts of material from Asia, and they're going into the West, and the ships are coming, and that demand is no longer there. And so, what do they have to do? They can't send the ships back. They have to actually create more warehouse space, convert their stores into warehouses to actually store those goods, quickly source supplies from people who perhaps are going out of business, and B, they have to come up with new suppliers. Now, an AI algorithm trained, and today we don't know how a machine could actually do these. Suppliers go out of business, customers repurpose. For example, auto companies quickly started making ventilators. So what you were shipping to an auto company, suddenly they're requiring different parts. So your again, meta learning is possible in the face of reinforcement learning. Many different ways of doing this. Causality, slow and fast learning. Daniel Kahneman, the Nobel laureate, talked about system 1 and system 2. Slow learning to learn the actual distribution as it changes, and to find the change in the distribution. Fast learning to optimize for the new distribution. But all that is not possible without data. And this is where very traditional science comes in, and you need. I hope enough time. I wasn't keeping track. Let's see. I think I'm okay. 5 minutes more, right? So good old IT, where you are modeling complex systems to build workflow engines, comes in very handy to build environments to simulate complex supply chains and enterprises and value chains, and use those simulations to train or meta-train reinforcement learning algorithms for a variety of different simulated situations, which and people who did that found that their RL algorithms are much more resilient, and people who didn't have these problems. The last point I'd like to talk about is when you try to deploy an AI system in the real world. Let's come back to that sort of invoice processing example. Obviously, you want invoices to be processed automatically. You don't want to have to check every invoice, otherwise what's the point of automating something? And let me ask you a question. I mean, an AI algorithm like that for processing invoice that is right 90% of the time, versus an algorithm which is sort of right 75% of the time. Well, the first one seems to be better. The trouble is you don't know which 10% it's wrong, but the second algorithm, if 50% of the time it could tell you with 99% confidence that it's right, well, then that 50%, you could just make sure that a human doesn't have to check it ever again. But for the balance 50%, you take a spot check, a quick validation by a human or by another technique. The second algorithm in practice is better, but machine learning literature focuses on the first. And the practical world, this dichotomy has not been properly addressed, perhaps by the academic community. And I think this is very, very important. So when we try to write papers, we also give the calibrations. Well, how often are you, and with what coverage can you actually say whether you're right or wrong? Deep learning is notoriously bad at this, but there are ways of fixing that as well. I'll end by saying, I'll talk a little plug about TCS research. We've been around since 1981. We have well over 500 researchers across 7 locations in India and a few in the US, across a wide variety of areas, in computing and the biological and physical sciences, advised by some senior people. And well, we do all kinds of research. AI impacts sort of all of it. And AI is pretty much just a bunch of useful techniques, and that's a question mark, because the expectation was that it tells us something deep about intelligence. The way at the boundaries, perhaps we know a little bit more, but whether we know anything truly significant, I have my doubts. Of course, in the current candidates, we also did a bit early on. We candidates with AI. You need to actually get that virus. You need to actually test it in vitro, then try it out in animals. All that requires a great collaboration between AI researchers and traditional biologists and others to actually do something useful. Thank you.
Thank you, Professor Shroff. Thank you, Dr. Shroff, for such an insightful talk. I think it was a lot more technical, and we get to learn a lot today from you. We may now take up some questions from the audience. I guess there were 2 or 3 questions. There is one which says that there is unsupervised pre-training is very popular these days, but there is very little consensus on whether these systems really understand useful representations that capture language characteristics.
I've also read many of these papers. There's Welling and there's Benju recently written a bunch of stuff. That's a very popular area. The question of whether it is really understand really goes back to the whole Chinese room paradox of Searle. That if you've been around, you would have heard of that, where you have a machine which sort of understands Chinese, of course, that it becomes an important, interesting example. Understand Chinese, and does it really understand the language? And it'll allow you, but you don't know. The only way we can do this is the utility. If the representations are actually better and generalize better in out of distribution, then we can say they're doing something a bit better than something else which is merely memorizing. But there's no other way, in my view, to tell whether something is better or not, because everything else is just speculation.
So one very interesting thing relevant to what Gautam mentioned, there is an article that appeared in AI magazine in 2020, which summarized the results of a workshop that was held, and the workshop was on crashing the barrier of meaning in AI. And it was authored by Melanie Mitchell, who is from Portland and Santa Fe. And it is an outstanding article, very resonates greatly with Gautam's remarks on trying to hybridize, in some sense, pattern-based learning with logic-based learning.
Okay, that's great. That's very interesting. There's a question. We'll take another 2 or 3 questions, relevant ones. One is, another one that has been asked is that what is the impact of these evolution in technologies on the health of the environment?
I don't know whether the environmental friendliness of having data centers crunching away very close to, say, a hydropower plant in the middle of nowhere, versus spending that carbon in a city so it chokes us. I don't know which is better. So that I'm not an environmental expert, but the truth is that even though we are spending a lot of energy there, energy is becoming cheaper. We just have to make sure it's clean energy. And that's the only thing I could answer in this question. But certainly it requires computing power, and computing power generates heat. Yeah.
And there's another question that, so I think we can take just 2 more questions. One is, what is a major role of AI in bioinformatics?
Oh yeah, so I gave you a couple of examples. So essentially, if you look at a molecule, small molecule like a drug or a large small molecule is good at docking into a protein can actually be done through a very complicated simulation called docking. It turns out that AI algorithms can very quickly, with reasonable accuracy, predict whether docking will work or not. So that the expensive docking, which can take days or to do per protein, can be done in seconds, so that you can scan a whole bunch of potential molecules which might actually attack a protein created by the virus, like the spike protein, for example, or the protease protein. And do that very rapidly. So you can generate lots of potential candidates which can be verified quickly. Secondly, for example, how a protein folds. Just recently, it's figured out AI has been, deep learning method has been able to predict the 3D structure of a protein, which otherwise could only be done using a very complicated physics-based device called a spectrometer. So I think there are a lot of applications in drug discovery and drug development, toxicity prediction, etc., etc.
Okay, there's one question from the industry perspective, which I think one of the attendee has asked, that how do you see the interactions of AI with humans in the workplace? Like, for instance, what happens to the change in the workplace dynamics, say 5 to 10 years down the line? This is more from the employment or job generation perspective. Do you like to answer this question, or we can keep it for later?
Well, AI does involve some amount of automation, and the kind of automation that it involves is the kind is sort of mundane sort of automation, and most automation so far has been like that from industrial revolution onwards. Every wave of automation, computer, obviously the armies of clerks sitting inside a big hall, which you used to see in the 70s and the early 80s, are no longer there. Doesn't mean that everybody's out of work. Everybody's doing something else. Whether I can predict what that something else is going to be, I don't know. But there will be something else because that's the way it's been, and this is fundamentally no different. And there will be new jobs and new ways of keeping. Jobs are essentially ways of doing productive work, but also ways of justifying the distribution of wealth in society. Both are goals of jobs, and society will create them.
I guess we can take the last question now. There is one with respect to the pandemic situation, which says that, is this current situation of pandemic an onset of the use of technology, although there is no production as such due to this situation?
Well, that's what I was afraid of, but there is production. The thing is that we still get our basic deliveries, and without that, in 4 months, production supply chain would have dried up. So there is production, firstly. Okay. And production is going to get more and more automated. Okay, and that's going to accelerate. The use of robots is going to accelerate even in small industries, because it's just safer. Not because it's cheaper, but because it's safer. It might be more expensive for them, but it'll be safer.
Okay, that's great. I think this was a wonderful, wonderful start by Dr. Shroff. Thank you so much, sir, for giving this very, very insightful talk.